I think we can pass to the next talk. The next talk, I'm sorry for my Italian pronunciation in advance, is from Kamyar Mohseni from the Instituto Tecnológico de Aeronautica in Brazil.
Yes, thank you.
He's going to talk us about three-boson stability for boosted interaction toward the zero range limit. And
exactly.
Please.
Thank you. Let me just share my screen.
You have half an hour together with questions, so that's 25 minutes.
Okay, just.
I think we just lost him, but hopefully he will be back. So in the meantime, okay.
Hi.
Hi.
Can you hear me? Great.
Yes.
Sorry, I had a problem. I think everything is set. Let me just share my screen. Great. Can you see my screen?
Yes, now it works.
Great. Thank you.
Thank you to you.
Good morning, everyone. My name is Kamyar. I'm from Iran, and I just finished my first year of the PhD at the ITA, and now I'm living here in the beautiful country, Brazil. I'm first should say that I'm really happy that I have a chance to work with Professor Tobias, Professor Hadi, Professor Andra, and Professor Diaz. As you know, today I'm going to talk about our previous work, that is the three-boson stability for boosted interaction toward the zero range limit. First, I'm going to talk about our goal. Second, we will look at the relativistic two-body, and for this aim, I'm going to talk a little about the separable potential that we use as a non-relativistic input potential. And then we use this potential as an input of our calculation and calculate the two-body relativistic binding energy. Then we will see the relativistic Fedov equation for the three-body bound state, and we will discuss the boosted two-body T matrix and boosted potential. I will present our numerical result for relativistic three-body ground and excited states, binding energy, and Fedov component of the three-body wave function. At the end of my presentation, I will summarize my talk. So, well, our goal. In our previous work, we wanted to study a stability of the relativistic three-body system in the limit of the zero-range interaction within Fedov scheme, and calculate the three-boson mass and wave function for the ground and excited state with Yamaguchi and Gaussian separable potential, and driving them toward the zero-range limit. Then we were interested to see how is the behavior of the Kamada and Gulukta boosted potential, which the boost concept comes from the moving two-body system in the rest frame of the three-particle system. So first of all, we should define the non-relativistic separable potential, which we use here. We use the for input of our calculation. One separable non-relativistic potential are generally defined as you can see in my slide. Left-hand side, we have a V subscript NR, which is the non-relativistic, in the momentum space and equal to lambda, which is the potential strength, multiplied to the form factor as a function of P, and another form factor as a function of P prime. In this work, we use two models of the separable potential, which was Yamaguchi type form factor, which defined as G as a function of the P equal to 1 over P square, P square plus beta square. And the Gaussian form factor GP equal to exponential of the minus P square over the lambda square. Which here with this separable potential, easily we can increasing beta and lambda to the large values and driving the potential to the zero range and contact interaction. Yes. By comparing the non-relativistic and relativistic Schrodinger equation and projecting the equation into the momentum space, we obtain this equation that indicate the relation between relativistic and non-relativistic two-body potential, which in the left-hand side, we have relativistic potential in the momentum space plus 1 over omega p and omega p prime, which omega p is defined as 2 square root of the p square plus m square. M is a mass and p is a relative moment. And then in the kernel of the integral, we have relativistic potential as a function of the p and p prime time relativistic potential as a function of the p double prime and p prime. In right-hand side is the 4 times mass of the nucleon multiplied the non-relativistic potential over omega p and omega p prime. Now we are going to calculate this non-linear equation. To calculate the matrix elements of the relativistic potential, we must do these steps. First, we must choose an appropriate coordinate system that we choose as a relative momentum vector p parallel to the z-axis and the p prime in the x-z plane. Second, for the discretization of the continuous momentum and the angle variable, we use the Gauss-Legend quadrature. And then using the iterative scheme with the initial guess that I show here, and then stop the iteration when the calculated relativistic potential satisfy this criteria with the relative error of the 10 power minus 10 at each point. The important and the vital point which proposed with the Komoda and Gluckle is the relativistic potential should reproduce two-body observables obtained by non-relativistic potential. As a numerical test for the relation between non-relativistic and relativistic potential, we calculate the relativistic and non-relativistic two-body binding energy. As you can see, here is the non-relativistic and relativistic Schrodinger Liebman-Schwinger equation for two-body bound state. As it's shown in the left-hand side of the first equation, we have a non-relativistic wave function, and the right-hand side we have 4 pi over two-body binding and two-body energy minus relative momenta square over m. And in the kernel of the integral, we have non-relativistic potential times non-relativistic wave function. In the second equation, for the relativistic wave function, we need to replace two-body energy to two-body mass, which defined as two-body energy plus the mass of the system. And in the kernel, we need to replace non-relativistic potential to the relativistic one. And non-relativistic, of course, non-relativistic wave function to the relativistic wave function. By this equation, I mean, Liebman-Schwinger equation and the relativistic and non-relativistic potential, we can calculate the eigenvalue equation and calculate the two-body non-relativistic and relativistic two-body binding energy. Here is a numerical test for the deuteron binding energy calculated by the Yamaguchi type 1 non-relativistic potential and constructed relativistic potential are that I showed to the, in this table. As we can see, the constructed relativistic potential reproduce the deuteron binding energy with high accuracy, and relative percentage difference, which is about 0.0, I can say 6 for Yamaguchi type 1 potential. Now I'm going to start to talk about the three-body systems. A partial wave projection of the relativistic Fedov equation for a system of the three equal mass particles in the momentum space and in the S-wave channel is given by this equation, which we have a Fedov equation or psi equal to the relativistic free propagator, which is 1 over three-body mass eigenvalue minus omega k p minus omega k. And then we have integral over the second Jacobi momenta and angle variable multiplied to the Jacobian function n times to the two-body boosted T matrix as a function of the two-body system energy epsilon, which boosted two-body T matrix is defined as a boosted potential V subscript K plus V subscript K, G, and TK. And then again, psi as a function of the shifted momenta, pi and pi t, which in the next slides I'm going to talk a little about these parameters. Sorry. Yes. In this slide, we can see the explicit form of the Jacobian function n, relativistic shifted momenta pi, and permutation coefficient c. We can see in the non-relativistic limit, Jacobian function and the permutation coefficient are equal to 1, and we can reproduce the non-relativistic result. Here I'm going to talk a little about the boosted two-body T matrix and boosted potential. Boosted two-body T matrix embedded in the three-body Hilbert space in the momentum space defined by this equation, which in the left-hand side, T subscript K is boosted potential, and in the right-hand side, V subscript K plus 1 integral over P double prime, and in the kernel, we have the boosted potential divided by the two-body subsystem energy, I mean epsilon, minus omega K times boosted T matrix again in the right-hand side. And here is the relation between boosted and non-relativistic potential, which is similar to the previous one. I mean, the relation between the non-relativistic and relativistic potential. But we should replace omega to the omega K to be able to reproduce to be able to calculate the boosted potential from the non-relativistic. As we discussed before, the boosted concept comes from the moving two-body subsystem in the rest frame of the three-body particle. So by this equation, the two-body boost interaction can be obtained in the term of the non-relativistic interaction. Now we can start the numerical to talk about the numerical solution. Here is our numerical implementation. First, we calculate the boosted potential from the non-relativistic separable potential by iterative scheme. The input of our relationship is a non-relativistic one. Then by having the boosted potential, we calculate the boosted T matrix, and in the end, we will be able to calculate relativistic three-body mass and wave function. In this slide and the next slides, I'm showing the diagonal matrix elements of the boost potential with different value of the boost momentum K, calculate for the wide range of the form factor parameter beta for the Yamaguchi type and the lambda for the Gaussian potential. Here in the top left, we calculate the boosted matrix element for beta 1. And here, solid red line is a non-relativistic potential. Dashed blue line is for K equals 0. Dash green is for K equal 10. And dash orange is for K equal to 100. And the maroon line indicates K equal to 1000. As you can see, the boosted potential are getting smaller by increasing the boost momentum K. And here I have another plot that show the same, but they are for the higher beta. Here we have a beta equal to 10. Here we have a beta equal to 100, and here is a beta equal to the 1000. And in this slide is the same as the previous one, but here we have a Gaussian time form factor. Again, for each of the lambda values, we can see the same as before. I mean, we can see the boosted potential are getting smaller by increasing the boost momenta K. In this slide, we can see the contribution of the different relativistic correction to the three-body energy calculate for the Yamaguchi 4 potential. As it shows a relative percentage difference for the Jacobian function n is minus 1.09%. The permutation coefficient is plus 1.02%. The relativistic three-body free propagator is plus 2.79%, and for the boost two-body T matrix is minus 4.73%. And when we apply all the correction together, we obtain a relativistic three-body energy of about minus 8.30 MeV, which indicates a reduction of about 2.4%. Yes. In this slide, I'm going to discuss about the stability that we expected to see with the Kamada and Gulup limit. In the left panel, I present three-body ground and first excited state binding energy as a function of the potential range parameter beta for the Yamaguchi potential and lambda for the Gaussian form factor. First, we see by increasing beta and lambda, the three-body system follows the Thomas collapse. Then the boost effects takes place and stabilize the system, which it shows zero range limit exists for the Gulup and Kamada boosted potential within the relativistic three-body frame. In the right panel, I present three-body and single particle mass ratio as a function of the two-body and single particle mass ratio obtained for three-body ground and first excited state using large form factor parameter. As it shows, as it's shown, our results with the large form factor parameter for both Yamaguchi and Gaussian potential reveal a universal behavior, and they are model independent. Our numerical results show a weaker attraction when compared to the result obtained from the light front and base submeter. And we believe that this effect can be explained by considering the slowest decrease of the three-body mass by decreasing two-body mass for the boosted potential calculation with the respect to the base salpeter and light front equation. And here in this slide, I present the FEDEV component of the wave function corresponding to the ground psi 0 and the first excited state psi 1 as a function of the Jacobi momenta p and k for two set of the small, I mean beta and lambda equal to 200 and large beta and lambda equal to 2000. For example, here in the top left panel, we have a ground state wave function for beta and lambda equal to 200, which red line is for beta equal to 200 when k is 0, dash blue is for beta 200, but for p equal to the 0, here k is not equal to 0 anymore. And dotted square line is for lambda equal to the 200 and k equal to 0. And red circle indicates lambda equal to the 200 and p equal to the 0. Here, the first thing that we can understand from this plot is that they are model independent. And the FEDEV component of the moment, they are model independence up to the moment about the beta and lambda that we use. And also we can see for large momenta, both potential models clearly show different decay behaviors. And the Gaussian model shows, as we expected before, the faster damping of the FEDEV component. As I said before, in the top right panel, we can see the same behavior, but for the larger, in the top right, we can see the FEDEV component, but for the first excited state. And in the bottom panel, also, we can see the same behavior of the FEDEV component, but here we have a higher value of the beta and lambda. Yes. And in the end of my presentation, I just want to summarize my talk and our previous one. In this work, we solved the relativistic three-boson bond state problem by using the Kamada and Gulukle framework and we built the boosted potential in the limit of the zero range interaction. The starting point for the relativistic and the boost interaction was the non-relativistic short-range separable potential, which we used the Yamaguchi and Gaussian form factor. And we drive into the contact interaction by letting their momenta scale to the large value in the comparison with the mass scale. And in the end, we saw the solution of the relativistic three-boson FEDEV equation with the boost potential are stable. And the three-body relativistic masses and the wave function are finite and model independence toward the limit of the zero interaction. And in our last plot, we saw that the Thomas collapse is avoided by considering the boost potential. And at the end of my presentation, I would like to thank my advisor and thanks to the CMP Q and FAPES and US National Science Foundation for financial support. And thank you kindly for your time and your attention. I would be happy to take any question and comments. Thank you.
Thank you, Kamyar.
Kamyar, yeah.
Kamyar. Sorry for my Italian.
No, it was quite fine.
Are there any questions about this talk? If there are none, I actually have a couple of questions. Oh, but we have a question. Is it?
Yes, I have the first question is that you avoid the Thomas collapse by putting Yamaguchi and Gaussian form factor, right? Exactly right. Okay, if you consider a zero-hand form factor G equal 1, then you have obviously the collapse.
Yes.
Is it right?
Here, I think, here we can see that for the high beta and lambda, we don't see the Thomas collapse, but for the low value of the beta and lambda, we can see our binding energy start to collapse. But here in this point, the effect of the boosted potential takes place and stabilize our system. Here is the plot that we saw that this model stabilize the Thomas and avoid the system from the Thomas collapse.
Okay, my other question is that you calculate in 3D, right? Is there any perspective to make this kind of calculation in 2 dimensions? Because my question comes from the idea that maybe in the relativistic case that you have -1 power in the kinetic energy, if you could have a similar kind of scale invariance like you'll have in 3D in a non-relativist case that you have Efimov states. Then if you, in the relativist case, if you have a -1 power in the kinetic energy, then if you consider the 2D case, then if you can have a kind of similar scale invariance, which could give similar results of the Efimov case in 3D.
Mm-hmm. Here in this work, we've worked in the partial wave projection. But our previous work before this, it was in the 3-dimensional space. Now we are working in the 2-dimensional. We are with another kind of potential. We are working the 2-dimensional, but I'm not sure that I can answer your question to if we implement all of this formula to the 2-dimension, can we see the avoiding Thomas collapse or another properties? Maybe I would ask Professor Tobias if he can hear me.
Yes, I'm here. Kamyar. No, probably it will be avoided in 2D as well. Probably, because the point is that you can see the boosted potential is weaker and weaker. And this you can already see from the boost. And this is why
I'm not considering this case, but if you consider a zero-hand potential in 2D,
yes.
Then you will have the same difference between the phase space power and the kinetic energy operator in the relativistic case, like you have in 3D and non-relativistic case.
But this case in 3D from the point of view of high momentum, is more singular than 2D, if you look to the kernel and so on. So if you reduce the dimension, and on the top of that, you have a weaker potential, boosted potential, so probably the collapse in 2D will not happen. I think is, I would say, no? That, I mean, non-relativistic, there is no collapse. But, I mean, the key point, I think, is the boost, is this boost potential. If you just put some kernel and you are worried that maybe you have the square root of p squared and so on, this will increase your kernel in the ultraviolet region or lead to scale invariance or something like that. I mean, this is only part of the game. It's not everything. I mean, you have in this kind of relativistic model, you have to make this boost of the potential to the rest frame of the three-particle system. And then when you have the third particle with very large momentum, the strength of the boost potential goes as 1/k. So you have even a stronger, I mean, depression, I mean. And this is what stabilizes in this calculation. At least is our understanding that avoids the collapse. But if you do also Bitzel-Peter equation, 4-dimension, we also did that. This does not collapse as well. Even with really with 5⁴ interaction, yeah, is here. You can see these are the results. So this is very essentially because, I mean, in part you have another scale, and the scale is the mass of your particle, and also in the ultraviolet, your two-body amplitude is weak compared to the non-relativistic one. So there are these subtleties that makes stable the system.
Okay, thank you.
Okay. So we have time just for another question, if it is very quick. If not, I actually have a very fast question. If you go back to your in the plots in which you show the different boost and the different interaction,
yeah.
Shouldn't be the red curve, the non-relativistic case, always coinciding with the zero boost blue dashed line case?
Actually, when k is equal to 0, we have the relativistic one. K equal, if we come back to this equation, when you put the k equal to the 0, this equation will be the same as this equation. So the k is equal to the 0 is exactly the relativistic one. Here we can see that the red line is a non-relativistic, but when the k is equal to the 0, when we are in the relativistic, the potential is a relativistic potential. The relativistic potential is below the non-relativistic one. But by increasing the k to go into the boost area, we can see by increasing the k, the boost potential decreasing. Okay. It's going to the repulsion.
So you expect the zero boost and the non-relativistic to not coincide in some cases. Okay.
Yeah.
Thank you.
Thank you.
So if there are no other questions, thank you to Kamyar. So then the next talk was actually of Rodrigo Alves Diaz, but eventually had some problem. I don't know if he succeeded in connecting to the conference. And since it looks that there are some problems, I suggest that we swap the two next speakers such that Rodrigo has some time to set up his connection, if it is okay for the organizers. So I will ask Samir if he's here with us.
Yeah, it seems that Samir is here. I mean, he's on.
Here.
Okay, very good, Samir.
Do you mind if we swap the two talks such that Rodrigo has some time to fix his connection?
Yes. Can I share my talk now?
We can see you. Okay. So the next talk will be for this swap from Samir Das from the University of Hyderabad in India, and he will talk about particle scattering by harmonically trapped quantum gases in artificial magnetic fields.
Yes.
So you have half an hour with questions, so roughly 25 minutes.
Okay, can I share now my talk?
We cannot see your screen.
No, you should share your screen, Samir. Click on the button. Yeah. Yeah, it's coming. Okay.
It is my great privilege. I am thankful to the organizer for the same. I talk about the particle scattering by harmonically trapped quantum gases in an artificial magnetic field. Now the brief contents of the talks as follow. I first discuss basic scattering theory, then I go the particle scattering by harmonically trapped quantum gases. Then I show the temperature dependent scattering, temperature dependent scattering cross sections for the scatterer in a 3D harmonically trapped geometry. Then I discuss about the particle scattering by harmonically trapped quantum gases in an artificial magnetic field, and then I show the thermodynamic property of quantum scatterer in an artificial magnetic field. Then references, and finally conclusion. The scatterings theory was important a long time before, after development of the wave mechanics. The scatterings is important to show the structure of matter. So it is example like the alpha particle scatterings occurs from the gold foil, first observed by Gazers at 1909. So we want to introduce the quantum scattering by quantum scatterers. Scatterer may be atoms or molecules in a when the scatterer not fixed, they are in a bounded regions in the space. The such work has been reported before. Example like diffractions of atom by a standing wave Schrodinger field, particle scattering by restricted geometry, etc. Now we want to introduce the temperature dependence of differential scattering cross sections for the scatterer is in a harmonically trapped geometry, how depend harmonically trapped geometry, where I take the interacting potentials as a Fermi-Hong potential. I consider the scatterer are inside a harmonic trap.
Samir, can I interrupt you? Sorry. I think that we have some problem in viewing your second slide is just half. So probably you have to scroll a little bit upper or put full screen your presentation. If not,
sorry, just.
Yeah.
Now, okay.
This is perfect. Thank you.
Okay. Suppose we take the incident particles coming along the z direction, so which is associated with 3 particles and scattered by the target. After scattering, they form the spherical wave. So this is the Schrodinger equation form, where the m is the mass of the particle and v is the target potential and is total mass. Then the very large r, very large distance. This is the asymptotic form of the total wave function. Where this is the spherical wave carries the 1/r factor. So absolute value of psi square. This goes to 1/r square to conserve the probability. Now the scattering cross sections, which is absolute value of f of theta phi square, which is important quantity to the experimentalist. So there are 2 techniques to calculate the scattering amplitude. This is the partial waves method. This is applicable only for the low energy scattering, where the first few terms contribute significantly, and another is Born approximation, this form, where the k dash is the scatter particle momentum, and k is the incident particle momentum, and this is v is the target potential at positions r0. Now the k dash in our calculations, the k scatterings scatter momentum is related to this, depend on theta and phi along the 3 direction. Now, sorry. Now I consider the particle scatterings in a 3D harmonically trapped gas cases. I take the normalized eigenstate of the scatterer for 1D harmonic oscillator, this form. Now consider scatterer are not fixed, having some relative motion with this particle. So the interacting potentials between the incident particles and the scatterer can be defined as this, where r is the positions of the particle and r0 is the positions of the scatterer. So if we calculate the f theta phi, this is the form. This due to this position shift, the phase shift is coming here. Now, so we take the scatterer moving along the x directions. So the x from minus infinity to plus infinity, all the possible point the particle should scatter, and corresponding this coherently corresponding probability density is this. So total net scattering cross sections according to the superpositions principle, this form. Now the scattering's amplitude depends on the three quantum number nx, ny, and nz, where the qx is this form and qy follow this and qz follow this, and lnx is the logger polynomials of order nx. Now, if you plot the d of theta phi, for constant phi, so take phi equals to 0, this theta number of node of oscillations depend on the nx plus ny plus nz along the theta axis. Now we should consider the scatterer in a harmonically trapped geometry at thermodynamics equilibriums with its surroundings having the chemical potential mu and temperature T. The scatterer may be bosons or fermions or the classical scatterer. So for boson, part at T equals to 0 Kelvin temperature, particle get together in the ground state, they form the condensate, but spin polarized fermion, they don't stay in the ground state. They repel to each other, follow the Pauli exclusive principle, and the scatterer are distinguishable by their the scatterer are distinguishable by their mass and the spin. We consider inside the harmonic trap, scatterer are particle, neutral particle. So this is the typical cartoon for the particle distributed in the various temperature region. This now our temperature dependent differential scattering cross sections form is this, where I replace here occupation number in nn. This minus here minus sign, this occupation number for bosons minus sign represent, and plus signs represent the fermion, and En is the energies of the scatterer in a 3D harmonically trapped geometry. So the scatterer is now their quantum numbers varies from nx 0 to infinity, ny 0 to infinity, and nz 0 to infinity. Now for harmonically trapped Bose gas, the scatterer in a ground state. So this follow this equation. As for fermion at T equals to 0 temperature, dTs follow this equation, and as scattering cross sections at K tends to 0, this is the form. Now we consider the harmonic oscillator is isotropy. So their length Lx equals to Ly equals to Nz, and Q square we replace Qx square plus Qy square plus Qz, and we take the Taylor series expansion of lnx ln is nearly 1 minus nx plus n into n minus 1 x square by 2 something, and we replace here the degeneracy n plus harmonic oscillator degeneracy n plus 1 into n plus 2, and now n varies from 0 to infinity. So in this way we can calculate the summation. Now this is the intensity distributions with theta for a single scatterer. For single scatterer's case, we replace the occupation number by probability, which is equals to e to the power minus beta en by of summation summation of z. Z is the partition functions, which is equals to e to the power minus of summation of e to the power minus beta en. Then the different temperature regime at T equals to 0 Kelvin temperature follows this line, and T tends to 10 to the power minus 7 Kelvin temperature. The dt varies this, and T equals 10 to infinity. This scattering cross section is infinitely narrow. Now now we take n equals to 10 to the power 4 number of particle at T equals to 0 Kelvin temperature. This is the variations. This is the variations of differential scattering cross sections with theta for Bose gas. This is Fermi gas, and this is for classical gas. This is infinitely narrow because the lnx is very large n limit. It is e to the power minus nx. It is itself polynomial, and we have taken all those parameters to draw this graph.
Yep. Samir, sorry.
Yes.
Can you repeat which angle is theta? I probably lost it in the last slide.
This data.
Theta, the angle.
Okay. I am taking the scattering amplitude depend only theta and phi. I take the constant value phi equals to 0, and this theta is related to the incident particle angle with that means it makes angle theta with z axis.
Okay, thank you.
Now this is the differential scattering cross sections variations with Tc. As for theta equals to 0, we get the dashed line, and theta equals to pi by 2. So this is this line, and for theta equals to pi, we get this. Now we have considered the interactions effect inside the harmonic trap between the scatterer. So we take the harmonic oscillator scale as L replaced by something new L. This new is the related to this. Then this new is the variational parameter. As this news variations with Tc is this form. Sorry. If I consider the weak interscatterer interactions effect and finite size effect, then the shift of Tc is this form from the ideal case, from this case to Tc this. Now I consider the different system, how to create the artificial magnetic field. Suppose the rotations of a system is the simplest technique to create an artificial magnetic field. Suppose the scatterer, the particles are moving along z directions in a rotating frame. So this in rotating frame, this is the Hamiltonian, where the m by minus m by 2 omega square or perpendicular square is the centrifugal potential, and I take the Q equals to 1, the magnetic vector potential can be represented this way for the symmetric gauge case. In the rotating frame, the Coriolis force acting on the rotating frames is equivalent to the Lorentz force, which can create the artificial magnetic field. So we want to calculate this 2D Hamiltonian. This want to calculate the eigenvalue of this 2D Hamiltonian. So we write the canonical positions and canonical positions at the momentum in term of the lowering and rising operator, and replace here. So we get the new Hamiltonian is this form, where A is AX plus IAY, and B is AX minus IAY. This led to ladder operator. After the transformations, we get this energy eigenvalue, where n plus as greater equals to 0, which is called the Landau level, and n minus is the Landau sub-level. For each Landau level, L plus plus minus is this form. Corresponding eigenfunctions of eigenstate is follow this, where A plus equals to this, and B rising operator, dragger of rising operator this form, and B dragger equals to this replaced by Z. Now we consider the particle scattering occur for this system as we consider the frames having same origin with the left frame and same z-axis and rotating along velocity omega k cap with respect to the left frame. So the Schrodinger equations in a for prime state represent this. All are the prime quantity. This is the angular momentums in the rotating frame, and this is interacting potentials in a rotating frame. Now we consider all the prime coordinate is all the prime elements is replaced by the unprime element, and very large distance. This is our scattering amplitude, where the phase factor is common so for both incident and spherical wave. This is the reference. So I take here. Now we consider the scatterings. Unfixed scatterer, which the particles could scatter all the possible positions such that R0 perpendicular varies from 0 to infinity, and phi varies from 0 to 2 pi, and z minus infinity to plus infinity. In these regions, the particle scatterings occur. Now the interactions between the incident particles and scatterer is this form. Similar way, we calculate the inelastic scattering amplitude due to transitions for the n plus state to n plus dash state and n minus to n minus dash. This is form here ki not equals to k. This is for inelastic scattering. So incident particle transfers some of kinetic energy to the trap scatterer, and their internal state of the scatterer are not same. After calculating this, we get this result, where zeta plus square equals to zeta minus square equals to q perpendicular L perpendicular square. So L perpendicular equals to h cut by m omega perpendicular and q z perpendicular this form. Now q perpendicular equals to k sine theta by 2 and qz equals to this form. So here inelastic scattering amplitude totally independent of phi. Very now very large N limit. We can calculate this form, and the asymptotic expansions of this follow this. Now similar way we can calculate the scattering amplitudes at finite temperatures. Before I did the dt's theta phi forms follow this, where plus sign represent the for fermion and minus sign for bosonic scatterer, and J is the fugacity of the scatterer. Now the at T equals to 0 Kelvin temperature, this is the differential scattering cross sections variation with the rotation speed. Here the discontinuities occur due to the transitions of the scatterer at the higher excited state, and this is quasi-periodic because we have taken the system is inhomogeneous, and at very slow rotating speed the scattering amplitude is larger, but higher rotation this shows the small scattering amplitude but with larger fluctuation. This is totally related to oscillations related to
recording stopped. Recording in progress.
This is totally related to the Fermi surface. Inter region of the Fermi surface scatterer get disturbed. Due to this disturbance, the fluctuations happen, and very high temperature limit DT is there is no oscillation effect. This work is published 2021 Physics Literary Journal.
You have 3 minutes left.
Okay. Now we consider the Hamiltonian is this. So where is the symmetric gauge field potential, and V is the harmonic trap potential. Now this total energy eigenstate follow this equation. Sorry, energy state follow this, where L is the confinement length in xy planes is this form, corresponding the energy follow this. Capital omega plus is this, and capital omega minus capital omega plus this. Now so similar way we can calculate the elastic. If we calculate the elastic scattering amplitude, the forms follow this equation, where the dt's depend on those quantum number, and the node of oscillations of the differential scattering cross sections. This depend on 2n minus m plus j along the theta axis. Now, if we take the differential scattering cross sections, that depend on the temperature. We introduce here the occupation number for bosons and fermion. Here m prime 0 to infinity, because here principal quantum number Landau level n varies from 0 to infinity and m varies from 0 to infinity. So n minus m's varies from 0 to infinity, which is indices by m dash. Now at T equals to 0 Kelvin temperature, this is the variations of differential scattering cross sections with magnetic field. The oscillations is controlled by B, and very higher magnetic field, we get the we get the envelope, and this discontinuity happen due to the inter-Landau's transition, and we can calculate the inelastic scattering cross sections before I did. So dt is varies with B is like this, where the jumps occur where there is enough number of particles to goes the higher excited state, and the quasi interval, because of the so we have considered the system is inhomogeneous. These oscillations related to Diaz van Alphen oscillations, there the magnetic field, magnetizations varies inverse of these periodically, but here we are getting the quasi periodically. Their systems is a homogeneous system. Finally, conclusion. In summary, I have analytically explored the quantum phenomena of particle scattering by harmonically trapped Bose and Fermi gases with short-range Fermi-Hong interactions among the incident particle and the scatterer. Fermi-Hong interactions, although easy to deal with, have huge applications in ultra-cold atom. We have seen elastic scattering cross sections, inelastic scattering cross sections. It's less probabilistic than elastic scattering at finite temperature. Both scattering process, the trapped fermionic scatterers, so the Diaz band-like oscillations, and Fermi energy has the most important contributions like electric, transport properties, optical properties of solid, and the inelastic scatterings. Here, here T is greater than Tc, the particles scatterer are in higher excited state, so rather than the ground state. So the coherence coherence reduces, and the dt decreases with increase of temperature. This happened due to the large angle scattering, but at T less than Tc, the particles all time in the ground state, at low temperatures, one can get the small angle scattering. Those are the references related to this work. And thank you, my presentation, and for your attention.
Thank you, Samir. Unfortunately, I don't think we have much time for questions. So there is any very impellant question that cannot wait. If not, I suggest to contact Samir personally, because if not, we are getting really late. Okay, so.
Samir, please stop sharing your screen.
Okay.
So if there is no other question, I want to thank again Samir. And we go to the last one talk of today, or becomes the last one now. So from Rodrigo. Rodrigo, are you here? Okay, hi.
Hi, good morning.
Good morning. So the last talk of today is by Rodrigo Alves Diaz from the Universidade Federal de Juiz de Fora in Brazil. And Rodrigo will talk us about Google TensorFlow in wave packets time evolutions. So the screen is yours.
Well, good morning for all. I will start to apologize because I was on vacation with my children and I make some mistakes and don't have time to create a formal presentation. So that we will do here is show you the idea that we have during some last months, and this idea is related to how can we use machine learning to give solutions to wave packets evolution, and we start to evolve the trading equation, and this project started when I was in UNB working with Professor Paulo de Brito, and is to take some wave function, an initial wave function like a Gaussian package, initial Gaussian package, and if this package we can evolve this package in a 1D, 2D, or 3D scenario, like scattering a wave packets in some particles in space. And I love this idea and starts to make programs to create this type of evolution using Fortran. When in 2017, I was in ICTP to a presentation of the Roger Melko quantum machine learning for quantum many-body physics. And in that situation, I learned about the machine learning, how to work with machine learning with physics. And I started to work with this. And I was so disappointed because I think that machine learning physics in that moment you give me some brilliant ideas, and I think, oh, it's only this. Oh, okay. So how can I create something different? And I learned the TensorFlow technology. It's a TensorFlow technology. It's a framework for Google for running with machine learning. Now I will project my my entire desktop share. I can, please, you are seeing my yes? Okay. So I start I forgot the line of processing. Okay. I was learning to evolve wave packets in time. So when I start to Google TensorFlow, I think, wow, this is a great idea to use TensorFlow to calculate metrics, because the ability of TensorFlow and these programs is basically to minimize some loss function and calculate the product of matrix. We can think in a neural net like a product of matrix. So to start the idea that I will show here, I will show you this equation. So easy equation for all of us. I think we have the Schrödinger equation and the time Schrödinger equation. So the Hamiltonian here may be a function of time and space. So if we create put the math to put these constants to here, we will have a time evolution operator. So the time PC dot the time the derivative of the wave function in time is only the application of time operator in a wave function in a given time. So if I have t equals to 0 in give some wave function in space like a Gaussian or like a wave, I can think a senoid, exponential, complex exponential, maybe the wave function that I want. You can evolve this wave function using the simplest method like Euler method. So you only need to calculate this one and operate. This is only the operation of the time operator in the given wave function. But I can do best for that. I use Runge-Kutta time evolution. Well, it's a time integrator that Euler is order of delta t square the error of Euler method that's so small, so we can use 4-order methods to evolve the wave function. Well, if I think that this count is something like this, you have a C point is only a matrix multiplied by a function. So in the language of machine learning, you have a wave function. Now you have weights, and you have this is this equation, yeah. But a new page. If I have this kind of equation, we can only give it. It's only the form of a matrix multiplication. But in neural net, what we have nodes, and this is we see in the time t. We have connections with bias that will be the function of my U operator. These connections in the language of machine learning is the called in the language of TensorFlow and this kind of it's omega c plus a bias. We can only give a wave function, give a time operator, that's the weights of the Keras model, and we can calculate here by C point. With this methodology, we can create many kinds of multiplications, or we create some deep, if you want, deep, how can I say, Hamiltonians to evolve, and we can create a time evolution using this approach. So we need only change the weights. Change the weights, it's equivalent to changing the Hamiltonian. So what I did, I create a Jupyter notebook. I planning to test the idea, so I create a Jupyter notebook, and with here is my contact. In this Jupyter notebook, I call the functions, appropriated functions for this one, and TensorFlow, Matplotlib, pandas to plot graphs. So now we create an input, a wave function. So the first layer is the real part of the wave function in space, like a graph.
Rodrigo, I have a question. Yep. So essentially, in all your nodes are wave function in a different time, right? And then you evolve them linearly using a matrix that is the time evolution matrix given by the Hamiltonian. So essentially, we are doing a sort of path integral with this
Yeah.
With this
in time.
Yeah, exactly.
Yeah.
Okay. So
I can think this when I start with this idea. I think this is a time evolution because I have the wave, the psi dots, the time derivative of the wave function. That's we have the time derivative of the wave function, so we can integrate this one. But we cannot think in this way. This is only a way to think, because I can think this like we enter a function. We have a wave function that I want. We apply the matrix that is the Hamiltonian, and I have psi dot. If I have psi dot, we can integrate like this one. Psi is psi plus psi dot that delta t with an integrator that I want. So we return this same wave function to enter in the same net, and this net calculates the psi dots and integrate this one happen until I want.
So essentially the net is something that you already know because it's your evolution matrix, right?
Yeah, it's kind of evolution matrix.
Why?
I don't want to learn in the first moment. In the first moment, I want to evolve wave functions. And using this approach, now, it's so easy. Yeah, it's a quite methodology way to do. But now, like, because I know that the TensorFlow can work with tensors of wave function of K1, C2 of K2, C2 of K. The number of inputs, the batch, in the language of TensorFlow, I can work with a batch of wave functions. You can think this one like a matrix, because I will evolve a bunch of wave functions, not one wave function. That this will act as a matrix with eights, and we will obtain here psi dot K1, psi dot K2, and evolve a bunch of wave functions.
So, but so for now there is no learning in this machine learning.
No, for now.
So okay, this is something that
I'm starting the project. This is only the idea to start with. I will create a quantum entity in the TensorFlow, and we will evolve then with some Hamiltonian that I can control. Okay. I can control this Hamiltonian in time or not, but I can evolve. But the next step is also we can evolve this package. I think it's a quantum machine thinking, evolving a wave function. I can put another wave, I think another neural net to control this quantum entity. Okay, you can think now you evolve a quantum system, and you can change some properties during the evolution of using a quantum machine, because my wave functions now are running in a TensorFlow that I can control a net or control another net. You understand the idea? Now I will show you some tricks that I have to perform, because you find TensorFlow in complex numbers. No, I don't have TensorFlow so easy using complex numbers. So using the keras, I want to use the keras because it's the most popular API for TensorFlow. So I think that I need to only to calculate psi dot, that is U T psi. So the Hamiltonian I write in this way. I will think this evolution operator U the real part of the evolution, plus I, the complex part of my time evolution, and the wave function, I have the real part of the wave function plus the complex part of the wave function. With this approach, that we need to perform these multiplications, and I will take a net that will be the real part. This is the CR, the real part of the wave function. This is a PCI with the complex part of the wave function. This is the nodes, and these nodes are connected in some way to obtain the same entity, CR point C E dot, and then we will evolve this one. Now I will show you some simple results. This is one thing that you can think about this net. But also we want PC dot. If I multiply PC with PC dot, we will obtain the energy, because we will obtain I will need to go here. Yeah, if you take psi square psi dot, you will have I psi square h psi over h, and this is the sum like E, the energy of my system. So you obtain the energy when you do this calculation. You giving some wave function, I can obtain the energy. So I can think this approach like to evolve, calculate PC dot, or to obtain the energy. Giving some wave function, giving one Hamiltonian, I can calculate the energy of a bunch of wave functions, and I can make intelligent choice of wave functions for giving some ansatz or some intelligent choice of systems. And to prove the idea, this is a project that I was starting. I create the input layer in TensorFlow or in Keras. This not so. So here we have input of real part of wave function, a real complex part of wave function, the connections that we need to create in order to evolve, and we obtain PC dot. The output of my model is exactly the PC dot real and PC dot imaginary. So we can make giving some wave function, we can give some measure. I will start to create STO2, STO1S, STO2S wave functions to test the system. And in this model, in this example that I will show you, I simply take the basic type byte model that the energy of the energy of the on-site of given band is constant, and I have a constant that connecting next near neighbors, and we give here. And now we create a wave function in a 1D system. This I give you an image of this. I take as a 1D system here, U of x. This is the x. I put a bar here of U0 with this width and put many different wave functions like this one with t equals 0 and x is a minus k dot r e meant alpha x and x to create some wave functions in some place that I can change the momentum, the initial momentum of this wave function in evolve this package to collide to this barrier, like a example. Once that I did this, we first calculate the energy. Where the energy, the graph of the energy. I know this is the image of the potential. I have a complex potential in the borders in order to wave function dot reflect, like absorbing boundary conditions, a two barrier in the middle, and we obtain the energy for many values of k values that I selected. I change this for positive hoppings and negative hoppings, and we can calculate the energy of a function of k and a function of the position of the packet. We can give some samples of the energy in the space that I want to use. The energy for some wave functions that I choose, which the answer of the wave function is the idea. This is the profile of the energy for many positions of as a function of the k values for that double barrier. And we have a movie to show. Where is the movie? Where is the movie? Oh, no, here. Here is a moving of. Here we have many. I think that's 1,000 wave functions located at that position with different k values. Now, since the k is changing, the different values of k running with different velocities, this one collides some functions return that reflected the fact the package some probabilities of different k values changing the amplitude of showing that different k values are changing different transmission coefficient, and in order to that we have a complex potential in the end, the wave function is not return because a complex potential works like absorbing a source or a drain, depending on that signal. And we can now, with this approach, since we have the time evolution of the wave function for different k values, we can calculate correlation functions of wave function in time. We can calculate all the properties that are intended. If you have a scattering problem, you can change many k values of the package to study the scattering of this problem. Here we starting with a 1D problem because it's more easy to understand. But since the difficulty is to write the correct weights to the the TensorFlow. So there is no difficulty because we know how we can connect next neighbors in a time by problem. And this is a project that are running. We started this in the 3 months ago. So the idea is to change this kind of problem to evolve relativistic and magnetic system in 2D, because we can think Hamiltonians like this one. We have a potential vector, we have magnetic fields, we have space potential, and we can apply magnetic fields, electric fields using this connection. And now in this moment, I creating a wave function, evolution, a model that can work with spin up and spin down and evolve all the two packets, this spin system, and study the interaction of this kind of system. In 2D, we can calculate magnetic. This is a work that I'm working on. It's this calculation of the expected value of the magnetization, showing if I have a magnet constant field, we can observe the precession of the magnet moments of that Gaussian package that I was evolving in time. And once we have this, the next step is to use another machine to control this entity. This is the next step that I'm working to. I hope that yes, great apology, because I know with a very beautiful presentation, and I want to show these ideas to a very selected public here. I'm so glad to be here, and we are thanks to the presentation, to the organization that taught me in the last minutes to remember. Hi, Rodrigo, you need to do a presentation. You remember it, and I hear, and so proud.
Okay, Rodrigo, I think you gave the idea. It's good to know. I mean, Lourenço is the chairman, and I already contacted you, but the title was quite interesting. Yeah. So I think you gave your idea, no? Maybe now Lourenço can take over.
Well, first, thank you. I know that is getting late there, but if there are questions about this idea or any comments from the public, it looks like everyone is looking forward for lunch. But actually, I have a question about this idea. So essentially, you are evolving in time your wave packet, expanded in multiple wave function bases. But why doing that in a machine learning machine? What is the advantage of using TensorFlow instead of using Monte Carlo in real time or discrete coordinate method?
In computational way, we can use any cluster of the Google or any cluster in the world to running big system. Because if you have a cluster with many GPUs, you can do very big calculation with a small amount of computation. We can create complex systems only changing the weights, or in a very simple method using keras. We can create many bigger systems and simulate this one using this approach, because this approach is very simple to create, and create some beautiful simulations and figures using quite nothing work to create this one. I think.
So essentially,
computationally gain, because the TensorFlow and this kind of systems are scaling velocity that are very assisted. Thinking
so
I'm meshing that thinking quantum. It is the idea, because you are evolving quantum system and controlling this quantum system using the same architecture, and you can create machines that learn a quantum machine. Do you understand? Because you can evolve that system in a biggest computers and clusters.
Well, as far as I understood, the power of TensorFlow and machine learning in general is the ability of readjusting the weights in order to self-learn something, but is not really the case. Actually, if I understood correctly, the good thing about this approach is that using the Google machine, you get a very optimized machine that does the work very fast without actually having to implement or having a high-performing computing facility dedicated to this.
Yeah,
there's a very good utilization of this kind of technique, although without the learning part of artificial learning.
But, the next step is to connect the learning part of that system, changing the Hamiltonian, changing the environment of the quantum system. The environment, I'm thinking the potential, external fields, a external machine that will control this quantum machine will now put I want to create a stage that these characteristics, put a field. It's like a qubit. I can think this is I can create a qubit and control these qubits with the machine. The idea is to create a qubit, because if you have the up contribution of the spins and the down contribution of the spin and evolve this entity, we can think this project a qubit like a component of spin up, a component of spin down, and instead this like you can think a qubit with projection. Yeah.
Okay. I think
I need more
time to think about
a complex entity that will process. I can create this quantity and evolve in a bidimensional system or three-dimensional system. To create a state and observe the evolution of the state and control this one.
Okay. Yeah, I think I need a little bit more thought about that. So thank you.
Yes.
Yep.
So thank you.
Thank you.
If there is no other questions except mine, we should call the morning also, because it's getting very late.
Yeah.
So thank you to Rodrigo, and thank you to all the speakers of this morning, and thank you again to organizer.
Yeah, thank you, Lorenzo. You made a great job. Thank you very much. So we meet soon. Okay, at 1 o'clock.
At 1 o'clock. Thank you.
Yeah.